If you've got objects blocking line of sight to your player and you're using the URP, this is the video you need to be able to fade those objects out using C# code. Hey, Chris here from LlamAcademy, here to help you.
Who, me?
Yes, you. Make your game dev dreams become a reality by allowing you to keep line of sight to your player. Now I know what some of you are thinking.
Why don't you just use a shader?
Listen, not all of us know how to use shaders. Some of us are very comfortable using C#. So what we're going to do in this video is look at how you can modify the material properties of a material in URP using C# and fade that object's alpha out over time. The benefit of this is you don't need to know how to use shaders at all. You can use the standard URP, lit, unlit, simple lit, all of the standard ones that come with URP, and this will work out of the box for you. That means you don't need to create some new shader to do whatever fancy shader effects you're going to do, to just have something fade out. I will say that the shader option is more performant, but maybe this is performant enough for your use case. It was for me in my game. Remember that the code that we're going to write today works specifically with those URP standard shaders. If you're using totally custom shaders or a shader not based on these shaders, it may require some tweaking. And I'm going to show you how in just 1 second you can check out how do you need to modify a shader to allow it to do this. Not all shaders support transparency and not all shaders support swapping between transparency and opaqueness. So that's something to consider, that this may not work for all shaders that you're trying to use. These ones just happen to be a kind of general purpose all-in-one shader that allows to swap between different modes. Some shaders may be only transparent and some shaders may only be opaque. For those shaders, this will not work. You'll need to either upgrade those shaders or use a totally different shader. I'm using the third-person character controller starter assets for the scene. We're going to be taking a look at the Universal Render Pipeline standard shaders, specifically the lit variant. If you're using more simple shaders than the lit one, it doesn't really make much of a difference. All of these are following the same pattern for how do they transfer from transparent to opaque and back. I'm not going to go through the entire process of how all of these were determined, but what you can do is follow the same process to see if you need to modify anything to make this code work for a different shader. Any shader that is based on these standard Universal Render Pipeline shaders, this should work on no problem. So I've opened up a debug inspector and a normal inspector window, so that way I can kind of toggle between the surface type and the blending modes and see what does that apply in terms of keywords and properties. We'll first see that with the opaque surface type, my keywords have emission, environment reflections off, and normal map. So I'll change this to the transparent and we'll see that a new element gets added, surface type transparent. If I add in then blending mode pre-multiply, we'll see alpha pre-multiply on is added to my valid keywords. I'll see that there's no new invalid keyword changed. If we then look at the string tag map, we'll see that the render type is changed to transparent. The render queue also changes. And there are some shader passes that change from depth only to shadowcaster. Those are two disabled shader passes that change whenever we enable the transparency. Finally, on the floats, there's a lot of them, so I'm not going to go through all of this, but basically what I did was open these, change them back and forth, and determine what changed from opaque versus transparent, and for my pre-multiply and alpha blend mode. So I've already created the scripts. We only have two to worry about today. That's FadingObject and FadeObjectsBlockingObject. We'll attach the fading object to any object that we would like to possibly be faded out. I'll also attach the FadeObjectBlockingObject script to the player. I notice I named this without an S on the first object. Let's open up Visual Studio and start implementing that fading object. In the fading object script, the first thing we'll do is implement the IEquatable interface of type fading object. We'll then implement the equals and get hash code functions here, and we'll implement them in just 1 second. First, we'll add a public list of renderers called renderers, a public vector3 position, and a public list material called materials. We'll also add a public float initial alpha that we're going to hide in the inspector because we don't want us to think that it does something if we set that in the inspector. Now that we have these variables defined, let's define how do we tell if this is the same fading object or not. We're actually going to do this based on the position, and this is to make it so this is very easily and quickly equatable, because in our FadeObjectsBlockingObject script, we're going to do a lot of equations with the fading object. So we want to have a very fast way to compare these two objects. So in equals, we will return position.equals other.position, and on the get hash code, we're just going to return position.getHashCode, relying on the vector3 implementation of of both of these. Now we'll really do the only piece of code we need to execute here, and that's on awake. We're going to do position equals transform.position. We're going to check if the renderer's count is 0. If it is, then we're going to add all the children of this game object as the renderers with renderers.addRange, get components and children, renderer. We want to do this so that way we have the option in the inspector to assign which renders should be affected, or by default, we'll just take all of them. Then we'll iterate over each renderer and add all of the materials of each renderer to our materials list. And set the initial alpha to be the first materials alpha. This is a limitation that we're intentionally implementing to make this kind of a little bit more straightforward. We're going to make all the materials fade, assuming fully opaque, to some target alpha, and then back to this initial alpha. If that's not your use case, then you could potentially have an array of initial alphas and have those mapped directly to the materials. It just becomes a little bit more complex for you to manage that. Now we'll open up the FadeObjectsBlockingObject script and create all of the variables that we're going to need. That's a layer mask, a transform target, a camera, a float faded alpha that will assign to 0.33f by default, a bool retain shadows that will set to true by default, a vector3 target position offset, and we'll assign that to be vector3.up by default. And we want this because a lot of the time the character controller position is at the floor, and we want maybe to offset wherever we're trying to raycast to from the camera to be maybe the middle of the player, or maybe we want to be slightly offset from the player. In this, I'm just using it for the height offset to move it off the floor to be about the midpoint of the player. We'll also add a float fade speed and set that to be 1 by default. All of those will be serialized in the inspector. That way we can manipulate them and assign them in the inspector. Now we're going to add a header saying read-only data to indicate to ourselves we should not be modifying these values below. And we'll add another private serialized list of fading objects called objects blocking view and assign that to be a new list by default. And we'll also make a private dictionary fading object to coroutine called running coroutines to equal a new dictionary of fading object to coroutine. Finally, we'll make an array of raycast hits called hits and assign that to be a new array of type raycast hit of size 10. I found that 10 is plenty for all of my use cases, but if you have a particularly complex scene with a lot of objects potentially obstructing your view, you can adjust the size of this. Just remember that the larger that you put this, the slower this is going to be. And the smaller you put it, the faster it will be. Then on start, we're just going to start a coroutine to check for objects. Let's define that with private IEnumerator check for objects. In here, we want this to run all the time, so we're going to do while true. And I'm just going to add a yield return null so it doesn't complain at me the whole time that I don't return something. And in here, what we're going to do is do int hits equals physics.raycast non-alloc because we don't want to constantly be generating garbage every single frame. This works the same as physics.raycast all, just without that garbage allocation. That's why we define the raycast hit array at the top. We're going to go from the camera position to the target position plus the target offset. So we're going to do target.transform.position plus target position offset minus camera.transform.position, and then we're going to normalize that vector to give us the direction. We're going to pass next the hits that will be populated by physics raycast non-alloc. We're going to check the distance between the camera and the target position plus the target position offset because we do not want to raycast farther than that because this will possibly return us false positives if we do that. A cool performance tip here is if your camera is a fixed distance away from this target and will never change, you can cache this and only calculate it once, and that'll give you a little bit of a performance benefit. And finally, we'll pass out the layer mask, so we're sure we're only raycasting on the layers that we want to be. If the hits is greater than 0, then we're going to iterate over all of those hits, and we'll do fading object equals get fading object from hit, passing in the hit at this current index. Let's go ahead and define that with private fading object, get fading object from hit that accepts a raycast hit, and we're going to return a hit.collider is not equal to null, question mark. That's like saying if hit collider is not null, then we're going to return hit.collider.getComponent fading object, and we're going to do colon null, which is saying else, we're going to return null. Back up in the check for objects coroutine, we'll say if fading object is not equal to null and the object's blocking view does not contain this fading object, then we're going to do another check if the running coroutines contains the key fading object. Then again, another check to check if running coroutines indexed by fading object is not null. If that is all true, then we're going to stop that coroutine. Outside of that if block, we'll do running coroutines.remove fading object. Now we're removing that coroutine from the list of running ones. And then I actually put this in the wrong place. We're going to move it in just a second. It's supposed to be inside that if, that outer if. We're going to do running coroutines.add fading object, and then we're going to start a coroutine called FadeObjectOut, passing out that fading object. Finally, we're going to do ObjectsBlockingView.add fading object. So we're going to add that fading object to the list of known objects blocking the view. So here I'm just moving it to the correct space. We're just moving it up into that outer if block. Outside of all of these, in the main while loop, we're going to add 2 more function calls that we'll address here in a second. One called fade objects no longer being hit, and one called clear hits. Clear hits is a private void, clear hits, and we're just going to do system.array.clear hits starting at index 0 for the length of the array. So that way we're just clearing all of them out. Before we define any more functions, let's talk about what's going to happen here. We're raycasting from the camera to the player, finding all objects in that path. We're seeing if we already know about this object blocking the view. If we do not know about this already, that means it's not in the objects blocking view list, then we check if we are currently doing something with this fading object, meaning we're running a coroutine to either fade it in or out, most likely out. We're going to stop that coroutine and we're going to remove that from the list of known running coroutines. Then we're going to start a new coroutine to fade out this object because now we know it's blocking the view, we need to fade it out. And then we're going to just add it so that we remember the next frame that we're already taking care of this fading object. With all that said, let's do private IEnumerator FadeObjectOut that accepts the fading object, fading object. In here, we're going to iterate over each material in the fading object materials. So that's for each material in FadingObject.materials. And what we're going to do here is exactly what you saw me kind of playing with in the inspector at the beginning, is we're going to set up the material to be transparent instead of opaque. We're going to set a bunch of ints. We're going to set the SRC blend, source blend, to be Unity Engine rendering blend mode source alpha. We're going to set the int DST blend to be Unity Engine rendering blend mode 1 - source alpha. We're going to turn off Z-Write and turn on surface. We're then going to adjust the render queue to be on the transparent render queue. We're then going to modify whether some shader passes are enabled. There's 2 that we care about here. One is depth only. We're going to set that to be false. And then one shadow caster, we're going to set that to be whether we want to retain shadows or not. We're going to set the override tag render type to be transparent. And then we're going to enable 2 keywords, one surface type transparent and one alpha pre-multiply on. What that means with this last one is that we're going to use the pre-multiply blend mode. You can optionally not do this, leave it alone, and you'll get the alpha blend mode, and then you can do some other stuff to get the additive or multiply blend modes. I find pre-multiply and alpha to be the best ones for this effect at least, so I'm going to use the pre-multiply. Now we've prepared the material for being transparent, but then we need to actually fade out that material. So we're going to do float time equals 0, and while fading object materials indexed by 0.color.a, that's the alpha, is greater than faded alpha, then we're going to iterate over each material in the fading object materials and say if the material has the property underscore base color. You're really wanting to use underscore color here because when we access the dot color property of a material, Unity under the hood is checking exactly that, the underscore color. We'll see that the URP standard shaders have both base color and color. I don't know why it has both, but because we're using the dot color on this material, we need to make sure that it has the underscore color property, not the underscore base color. Then adjust the alpha of this material to start going to that faded alpha with material.color equals new color, keeping the RGB values and then doing mathf.lerp, passing in the initial value being FadingObject.initial alpha and going to the faded alpha over time times fade speed. So as we increase fade speed, this will go more quickly. We'll then, outside of the for each loop, but inside the while loop, do time plus equals time.delta time and yield return null. So we'll do this every single frame. Once we fully faded out this object to however faded out we want it to be, we're going to check if the running coroutines contains this fading object, which it probably does. We'll then stop this coroutine and remove it from the running coroutines list. Next up, let's do the inverse, where we're going to fade an object in. We're going to define a private IEnumerator FadeObjectIn that accepts the fading object. And what I'm going to do is actually copy paste exactly what we just did in FadeObjectOut to give me a good starting point. I'm going to reorder that while loop at the bottom to the top because we want to go in the exact inverse direction where we first fully fade in the alpha of this fading object and then set the material properties back to opaque. Which means at the top here, we're going to do while fading object materials indexed by 0.color.alpha is less than the fading object.initial alpha. And then we're going to do mathf.lerp from the faded alpha to the FadingObject.initial alpha. The rest of this will stay the same. And then we're going to iterate over all the materials again and just go kind of the inverse way. So the source blend should be 1. The DST blend should be 0. Z-Write should be turned on. Surface should be turned off. The render queue should become geometry. The depth only should become true. Shadow caster should be true. The render type should be opaque. And we want to disable those keywords that we enabled about being transparent and having alpha pre-multiply on. Here at the bottom again, we need to do the exact same thing we did before with if running coroutines contains fading object. Then we're going to stop that coroutine and remove it from the dictionary of currently running coroutines. All right, all the hard stuff's over. There's only one function left to write. Let's go ahead and write out fade objects no longer being hit. We already kind of talked about what we're going to do, but we haven't implemented that yet. That's going to be a private void fade objects no longer being hit. We're going to create a list of fading objects called objects to remove equal to a new list of fading objects of size objectsBlockingView.count. Since we're defining some new variables here, we don't want to resize the array. So we're going to make sure it's already big enough to house whatever it is that we need. We'll then iterate over all the objects blocking view with for each fading object in objects blocking view. We'll define a bool object is being hit equal to false, and we're going to check all the raycast hits to see if this object is being hit. With fading object, hit fading object equals get fading object from hit, hits indexed by I. And we'll check if the hit fading object is not null and the fading object equals the hit fading object. Then we'll say object is being hit equals true and break out of this loop because we found what we're looking for. We'll then check if the object is not being hit, then we're going to check if the running coroutines contains this fading object. If it does, and the running coroutines of this fading object is not equal to null, which is most likely, we'll stop that coroutine. Outside of that check, we will remove this fading object from that dictionary of running coroutines. Outside of that if, but inside the not object is being hit, we will do exactly as we did before, running coroutines.add fading object, start coroutine, but this time fade object in, passing in the fading object. So we will then fade this object back in from its faded state, and we will do objects to remove.add fading object. Outside of all of these loops at the root level of this function, we're going to do for each fading object, remove object in objects to remove, objects blocking view.remove, remove object. And that's all the code that we need to do. Most of this is coroutine management. The key pieces that we saw were fading the object out and fading it back in. I want to take a second to give a huge shout out to all of my Patreon supporters. Every one of you is helping this channel grow, reach more people, and add value to more people, and that helps more people make their game development dreams become a reality. If you've been getting value out of these videos, consider becoming a Patreon supporter. Go over to patreon.com/LlamAcademy, get your name up here on the screen, get a voice shout out starting at the awesome tier, and some other cool perks at the tremendous and phenomenal tier levels. Speaking of the phenomenal tier level, I have Andrew Bowen, and at the awesome tier, I have Gerald Anderson, Autumn K, Matt Parkin, and Ivan. Thank you all for your support. I am so grateful. Back in the Unity editor, I will select my player armature that has the fade object blocking object script. I'll drag the player to be the target. I'll drag the main camera reference, and I'll set the layer mask to be the floor. I'm going to leave everything else as the default so we don't have to worry about it, and I'm going to click play. Once we get in here, I'll run behind this cube that we attached the fading object script to, and we can see that it fades out as it blocks view to the player. Perfect. I will say that the fade speed of 1 is relatively slow. That means that it's going to take 1 full second to fade all the way in or out. So if you kind of run back and forth between something really quickly, it's a little bit jarring because remember that it starts at the fully faded out or the fully faded in alphas. If we adjust it to have a fade speed of 3, we'll see that it's significantly faster, kind of a better feel. If I turn off the retained shadows, you'll see what I was talking about with the shadows just kind of disappearing all of a sudden, and then some weird other behaviors, like I can see the shadows from the stairs above me. That's not ideal. And we can put our camera even inside something and it's still catching on stuff correctly. So that's pretty cool. You may notice this works only with a very thin ray from the camera to the player. Sometimes you want to maybe pre-fade some object as your player gets closer to being behind there, so that way you don't have to wait for the player to become obstructed before you start fading. In those cases, you may consider doing something like SphereCast non-alloc, which is also really good, but slightly less performant. I'm thinking generally in your game, you're only going to have one of these active, so if you're doing 10 sphere casts in a frame, or every couple frames if you do this with like a throttled frame rate, it's probably not that big of a deal. However, if you decide to put in a bunch of these, then we start getting into some performance concerns that you need to address. I know it seemed like there was a lot of code in this, but most of that was coroutine management, making sure that we were keeping track of which fading objects had which coroutine associated with it so we could appropriately stop them. The really core of this, remember, was only 2 steps. One is update the material properties to be either transparent or opaque. And the other step was fade it either in or out, depending on which direction we're trying to go. The ordering of these is important too. You want to make sure you transform the material from opaque to transparent and then fade it out. And going the other way, you want to fade it back in and then transfer it back to the opaque material properties. Like I said at the beginning, using strictly a shader to manage the visibility of these objects and cutting holes in them or something like that is probably a more efficient solution. I found this very easy to implement and very convenient because then I didn't need to use a bunch of different shaders. I like to keep the shaders kind of straightforward. Again, mostly probably because I don't know very much about shaders. I still haven't dove into that yet. Anyway, if you got value out of this video, please consider liking and subscribing to help the channel grow, reach more people, and add value to more people. There's new videos posted every tutorial Tuesday, and I'll see you next week.